All right, let's take a look at our lesson for today. So today we're going to be looking at the extreme value theorem and the candidates test. So let's focus first on the extreme value theorem. What this tells us is basically if our function is continuous over a closed interval, okay, so if it's continuous over the closed interval, then the function is going to have at least one minimum value and at least one maximum value. So let me be even more specific. When they say minimum, just use the word minimum, they really mean absolute minimum. That's really important because we do so much work with relative minimums that sometimes we assume that's what they're talking about, but that is not. It's an absolute minimum. Okay, so that's something to note for extreme value theorem. So if it's continuous on the closed interval, we have at least one max and one min. And the value, and this is also they're very picky about this, the value is the y value. They are really interested in the y value. Not necessarily the x value, that may or may not, but the y value is called the maximum value. So really important for us. Okay, so that's extreme value theorem. Critical points. So we have something called critical points, and that's where we take the derivative. So let's kind of focus on this. So we've got, it's in the domain. So we're in the domain of the function. And the critical points are where the first derivative is 0 or the first derivative fails to exist. Okay, so that would be like the first derivative is d and e, does not exist, or the first derivative is 0. That's called a critical point. And we use these really frequently, these critical points. We use them frequently to determine maxes and mins, all kind of things. So it's really important concept for us. But want to note that there's two kinds. Now, I really kind of go a little crazy, and they have names. This kind is called the stationary point. And this kind is called the singular point. And the reason I make a big deal out of their names is because the poor little singular points are usually forgotten. Poor little things. They usually are forgotten. So I really make a point to call out their name, the singular point. That's a kind of critical point. There are two kinds of critical points. There are stationary points and singular points. Stationary is where the first derivative is 0, and singular is where the first derivative is undefined. And that's the basis of what we're looking at today. Okay, we okay with that? All right, before we start the examples, I want to look at this graph over here, this diagram, so we can talk about the differences between local and absolute maximums and mins. There is a difference. So since we talked about the extreme value theorem and we talked about absolute, why don't we just start there? So an absolute minima or maximum means that there is no greater value of f. There's no greater y value on the whole interval. It is the very largest y value. It is the largest y value on the interval. Now, this type of absolute max where it occurs in the middle is also a local maximum. Okay, so it kind of doubles its usefulness. It's also called a local maximum if we are, inside here. Okay, that's an absolute. So an absolute minimum is for absolute minimum, it's the very smallest. It's the very smallest y value on the interval. And absolute extrema can occur at the endpoints. You'll notice that this one occurs at the endpoint. Okay, that's okay. Relative extrema cannot occur at the endpoint. Okay, notice how this absolute maximum has double use. It's an absolute max and a local max. But notice how this absolute minimum does not have a double use. It is not also a relative or local minimum. It's just absolute. So let's see what the difference is. What are these local or relative? They usually use both those words. So local or relative maxes and mins. What is their deal? Basically, the best way I can think to explain it is it's kind of like mountain tops and valleys. Right? It's kind of like if you're standing right here on the top of the mountain, you are at the highest point in this general area. If you look to your left, you see something lower. If you look to your right, you see something lower. It's the greatest value nearby. There isn't any bigger value of y or of f nearby. That is a local or relative maximum. The same thing happens with the local or relative minimum. So it's as if we're standing in a valley. We're standing right here, and I look to my left and I see points bigger than where I am. I look to my right, I see points bigger than where I am. And so that qualifies as a local minimum, local or relative minimum. There's no smaller value of the function right nearby. So now let's re-look at this one and see why is it that this can only be an absolute minimum, this point right here. Why can't it be a relative minimum? Well, as I look to my left, I see that, there are bigger values over here, but as I look to my right, there is nothing there. You see, there's nothing there on the right. I can't make that judgment. I have to be able to look both right and left to determine whether I'm the lowest y value or the highest y value. So this is why you can't have a relative or local min or max on the endpoints, because you don't really know what's happening on the other side. Does that make sense? You just don't know. So I don't know, maybe it goes up from here. I don't know, or maybe it keeps going down. I mean, who knows? We don't know, so we can't say that it's a local minimum, only an absolute. So that's kind of a long explanation on the differences between local and absolute maxes and mins. Are we okay with that? Okay, so now with that information, let's work on the examples. This first example is asking us to find all extreme values. Now, they're not specifying, so that means absolute. Okay, if they don't specify, they're talking absolute. Just something you're going to have to memorize, unfortunately. Okay, so we want to identify, where they are, what they are. So let's look. We've got the very tallest y value looks to be right here, right? That's the very tallest y value. So that is going to be our absolute max is, and it's that y value 5. Okay, so many times we are tempted to put the x value, and I know we really are all about x's, but it's the y value. Now, we can give additional information. And we can say that this occurs at x equals 0. The maximum y value is 5, and it's at x equals 0. That's fine to include that, but we have to actually name the maximum value as the y value. Okay, so now let's look to see about absolute minimum. Looks to me like this y value right here is the very smallest y value on the graph. So I'm going to say absolute minimum equals 1. That's the y value at x equals -3. Now, we could look to see if there's any relative extrema. Let's see if we can reclassify things as relative. Now, of course, no endpoints won't count, but what about this one right here? What about this one up here? Could we also classify that as a relative or local maximum? We can, can't we? Because if we look to the left and the right, everything is lower on either side. Does that make sense? So yes, we could totally say that we have a relative maximum at 5. That's the y value, and that occurs at x equals 0. So we do have a relative max. Do we have a relative min? We really don't. We don't know what's going on the other side of that point at x equals -3. We don't know. And it's not continuous, so it doesn't have to satisfy the extreme value theorem. If the extreme value theorem was satisfied, we would have to have, well, actually, we do have an absolute max and absolute min here. But it's not, because it's discontinuous right here, right? And it's got a hole right there. So this one is a little bit weird. Okay, are we okay with number 1? All right, let's look at number 2. So let's start with our absolute extrema first. Let's see if we can identify what the very biggest x value is. Y value. So it looks like that's right here. So we've got an absolute max at 3. The y value is 3, and that maximum value is at x equals -1. Okay, that's good. Do we have an absolute minimum? This looks to be the lowest part of the graph, but it's a hole. There's a hole there, so I never can get to it. So unfortunately, this one does not have, there's no absolute min. Which it can happen, right? This is not guaranteed by the extreme value theorem because there's a discontinuity. So we don't have to have one, and actually we don't. All right, so now let's turn our thinking towards relative. Do we have is that absolute max also a relative max? Is it the tallest in that general area? It is, right? So we also have a relative max, and that relative max is 3, and it occurs at x equals -1. Okay. And if we want to further clarify where there's no absolute min, we can say because of the hole, if we wanted to, because that's really why there's not one, is because there's a hole there. All right, so this is some examples on just reading this information off of graphs. We doing okay? Okay. So the next thing I want to do is we're going to focus on finding critical points. Remember, there's 2 kinds of critical points. There's the singular and the stationary. The stationary is when f prime is 0. The singular is when f prime is undefined. Okay, those are the ones where we always look for both. We may not have both, but we always look for both. So what am I going to have to do? Well, I'm going to have to find the derivative and set it equal to 0. Okay, so we're going to get some derivative practice in here. So what I would like to do to make my life easier is I would like to rewrite this g of x first so that I don't have to do quotient rule. I know I'm probably hurting quotient rule's feelings. I'm so sorry. But if I can avoid quotient rule, I will, because it takes much longer to do. So instead, I'm going to rewrite this as 4 minus x squared to the -1/2. Okay, that's just going to make my life easier. The 1 that was in the numerator is basically just sitting outside here, so we don't really even need it. So that's just going to make my life easier. Now, instead of using quotient rule, which inside of quotient rule I would have to use the chain rule, now instead of having to do that, I can just use the chain rule, right? Let's just do our derivatives. I would bring the -1/2 down, copy paste what's inside, subtract 1 from -1/2. -1/2 minus 2/2 is a -3/2. Then I would multiply. If you remember, we'd have to chain this. I would multiply by the derivative of the inside. Okay, so the derivative of the inside, derivative of 4 is 0. The derivative of negative x squared is what? Negative 2x. Okay, and that's my derivative. Now I'm going to have to set it equal to 0, and it's really just a big mess. I don't really want to mess with it like this. I need to pretty it up before I try to set it equal to 0. So let's rewrite it, just get it looking a little bit better. So let's see, the negative times the negative, it turns it positive. The 1/2 and 2 turn to 1. And then I'm left with what? I have x in the numerator, and I have 4 minus x squared to the 3/2 in the denominator. So when we're looking for critical numbers and we have a fraction, just a shortcut, if you will, I'm going to set it equal to 0, right? I'm just going to do this now so that I can explain why I'm getting ready to do what I'm getting ready to do. So when I set a fraction equal to 0, do we really care what the denominator is as long as it's not 0? We don't really care, right? Because 0 over 5 is still 0, 0 over negative 2 is still 0, 0 over 2,000 is still 0. We just really want the top to be 0, right? So what I do is I set the numerator equal to 0, which just happens to be 0, and I set the denominator equal to 0 because the denominator is going to give me, so this is going to give me my stationary points, and this is going to give me my singular points. The denominator equal to 0. Okay, so we raise each side to the 2/3. And I get 4 minus x squared is 0. And so 2 minus x, 2 plus x. So x is plus or minus 2. Now before we declare this as our stationary points, we need to verify that it's in the domain of the original function. Okay, in the domain of the original function. So I'm going to go back here. I'm going to look at this critical point business, right? See, I highlighted that in yellow. The critical point has to be in the domain of f. That is a really big deal. It has to be a critical point, it has to be in the domain of f. All right, so let's look at these values. I have 2, positive and negative 2. Are those in the domain of this original function? If I put a 2 in here, would I be okay? If I put a 2 in here, if I did 4 minus 2 squared, that's 4 minus 4, that's 0. Is that okay? Is that okay to have a 0 in the denominator? No, that is not okay. So plus and minus 2 are not in the domain of the original function. So these are not in domain. So they're not considered critical numbers. Now, they are points of interest. And I'm going to just re-clarify. It's not that they're not important. They are points of interest. Why would we be interested in them? Because they're where the original function doesn't exist. We should be interested in them. They're just not considered critical numbers. They're not considered critical numbers, but we are interested in them. Okay, and we'll learn later why we would be interested in them. Is that okay? Okay. Are we good? So that's critical points. Okay, so we actually just have one. We have one critical point, and that is at x equals 0. That's all we have in this for this function. Okay. So let's look at the second topic in our lesson, and that's candidates test. So we looked at extreme value theorem. We talked about critical points. Now let's look at candidates test. So candidates test is, just something you're going to have to memorize. Yes, it appears on formula quizzes. It's a 3. So What has to be true? Okay, so here we go. For candidates test, what do? We find the y values of the critical points in the interval. Then we find the y values of the endpoints A and B. And we test them. So this is the candidate's test. The largest y value is the max, and the smallest y value is the min. And that's the candidate's test. What do we use it for? We use it to find absolute extrema. That's what we do. This is our test. It's the only test we use to find absolute extrema. It's called the candidate's test. You're going to be super familiar with it before too long. Okay, so how does it work again? Okay, we find the y values of the critical, we find the critical points. We find their y value. I put them in a table. We find the y values of the endpoint. I put it in a table. And then I look at the y values and I pick out the biggest y value. That's like the winner. That's the max. And then I pick out the smallest y value. That's like the winner. That's the min. Okay, that's how the test works. It's really not bad. You just have to remember how to do it. So we're going to practice that.
So to find a critical point, you take the derivative and then you set it equal to 0?
That's correct. Yes, critical points are where you take the derivative, set it equal to 0. So you would do that first, and then you would test the value. Okay? All right. And so let's be even more specific about which y values we're looking for. These y values, because this sometimes confuses people, these y values come from f, not f prime. Okay, these are y values of f, not of f prime. These are y values of f. Okay, the y values, what we do when we find the critical points and the endpoints is we put those values, those x values, into the original function, and that's how we judge who's the winner and who is not. Okay, so that's our test. So now we have one example on, we're gonna do the test. We're gonna find the test. We're gonna work through the candidates test. All right, so it says find the absolute maximum and absolute minimum value of that function. It's a polynomial on this interval. Okay, so this is important. This interval is that's the one we're working with. Okay, so let's look at the candidates. Let's find the candidates. So I'm going to start a table over here where I'm going to list my candidates. Really, this is the best place to organize your candidates, is to just get them all in one place. It will help you in the long run. I know that the endpoints are candidates, so I'm going to write them on here. -1/2 and 4. And to find the y values, we're actually going to go to a calculator. We're going to go to the calculator, and I'll show you another thing that we can do that would be helpful. Okay, so I need my critical numbers. And remember how we find the critical numbers? We take the derivative, set it equal to 0. So let's do that. So f prime of x. So the derivative of x cubed is 3x squared. The derivative of -3x squared is -6x. And the derivative of 1 is 0. Okay, so we set that equal to 0. And I'm actually going to factor, because that seems like that would make my life easier. I'm going to factor out the GCF, the greatest common factor of 3x. And that leaves me that. Okay, so my critical numbers are, so I would set each factor equal to 0. 3x equals 0. X minus 2 equals 0. So solving that, I get x is 0 and x is 2.
Sorry, could you say that again?
And that was exciting, yes. I don't think I said series, did I? No, I don't think I did. Okay, so here are our critical numbers. We're going to add those to the list. Okay, is everybody good? So what I'm going to do is I'm going to show you another way to store that function in your calculator and make your calculator do all the work for you. Now, just as a reminder, if I was doing the work myself, this is a reminder, we're not going to do the work ourselves, but I'm just reminding you, I would take the negative 1/2 and I would put it everywhere there was an x, and I would do all of that arithmetic. Okay, if I was doing it by hand, that's what I would do. Right, we're familiar with this. We've done this numerous times. I'm plugging it back into the original, right? We go back to the original. So I would stick in the negative 1/2 and go to town. Now I'm going to go to the calculator. We're going to do it a different way. So if you have your calculator handy, it might be a good idea to get that out. So we're going to do this a little bit different, which will hopefully make your life easier. So I'm going to just do a calculator page. Okay, I'm just going to do a calculator page. And I'm going to type in the function. So the function was, what was it? X cubed. So X cubed. Then we were, what were we? Minus 3x squared. And y'all may already know how to do this, but some of you may not, so I'm just going to show you. Minus 3x squared plus 1. Okay, so what I'm going to do is I'm going to store that as a function. Okay, see this little blue store button right here above the VAR? I'm going to do Control VAR. I'm going to do Control VAR, and see how it puts a little arrow there for me? And I'm going to store it, I'm going to call this, why don't we just call it f of x, because that's what they called it. I'm going to call it f, and I have to do the of x, or it's not going to recognize it, and I have to use this x. I have to call it f of x, like that. Okay, that's what I'm doing. I'm calling it f of x, and I hit enter. So now that's where it is. So if I want to find f of negative 1/2, they store it in this button that says VAR. See the VAR button? If you click that button, it's right here. It's called F. F of, and I'm going to type in negative, and let's just do 1/2. And I just hit enter. And that's the value that I would have gotten had I done all that arithmetic. You with me? Way easier to do than actually physically plug it in your calculator. I would recommend that you learn how to do this if you don't know it already. So I have other candidates that I need to do. So let's do the other candidates. So we need f of, let's see, what is one of the other? 0. We need f of 0, and that's 1. We need f of, let's see what else we need. F of 2, and that's negative 3. And then we need f of, what did we need? F of 4, and that's 17. So that makes our life much easier. Okay, are we okay with that? Okay, so those are my values. I'm going to go back over here, and let's write those in the, let's write them down. So the negative 1/2 was 1/8. The 4 was 17. The 0 was 1, and the 2 was negative 3. Those are all of our candidates. Okay? So now we do the test. So I'm looking at all the y values, and I've got to pick out the very biggest y value. The very biggest y value is right here. Right? That's the very biggest y value. So I'm going to say absolute max equals 17 at x equals 4. So they have the information. Any information they need, they've got. Okay, now let's go through and pick out the very smallest y value. Okay, the very smallest y value is right here. So we're going to say absolute min is negative 3, and that occurs at x equals 2. And that's my answer. So this is your answer, and this is your justification. This is a justification. This is candidates test. And you don't have to say candidates test if you don't want to. It's not required. You don't have to call it candidates test. You just have to show it. So this is all justified with this table of values. And you actually get points for finding the candidates. So it's really important that you actually find all the candidates. Okay? All right, so that's our very first candidates test. How are we doing? All right, the last example I'm just going to have to admit to you is a very strange example. It's very highly conceptual. This is highly conceptual. We just saw how to do the candidates test with an equation. It's pretty straightforward, right? We find the derivatives, set equals 0, get all our candidates, test them in the function, good to go. This one is more abstract. We're going to look at the graph of f prime, and we're going to try to figure out if we can find out what the absolute extrema is. Okay, we're just going to look at it. So we haven't really talked much about area before under the curve, have we? Okay, so let's talk about it. It's just something to talk about. We'll really be dealing with this next semester with integration, but it's a concept that we need to understand. So if I am traveling forward, which we're going to travel forward, the area above the x-axis is positive, so I'm going to make it, I don't know, green, I guess. Let's make this green. So this is all positive area. The area, and there's more positive area right over here. That's positive. The area under the x-axis is negative. That's negative. And it's literally area. We can actually approximate the area. Now we're going to learn special techniques to approximate the area. But right now, we're just going to do just a big approximation. I'm going to say this is like, I've got 1 box, 2 boxes, 3 boxes. We'll call this, I don't know, that's about 4, 5, 6. Okay, I'm going to say that's about 6 boxes. Again, we'll learn a much better technique later. That's about 6 boxes. Underneath here, that looks to me about, I don't know, maybe 2 boxes. And on the far right, we're going to say that's maybe 1 box. Okay, maybe 1 box. So we've got the boxes. The boxes are going to represent, they actually are going to represent function values, which we will learn next semester. But this is just a preliminary look at it. This is very highly conceptual. So when I'm looking for absolute extrema, I'm still looking at the candidates. Okay, I'm going to write and we don't even know the values of f. We don't know what they are, but I'm going to write down the candidates. So the candidates are the endpoints. So I've got -3 and 4. And they're also the critical numbers. The critical numbers are where f prime equals 0. Is there anywhere on this graph other than the endpoints where f prime equals 0? You got it at 3 and at 1, right? F prime equals 0. So those are candidates. And literally, the absolute extrema can only be one of those 4 places. And it has to be in one of those 4 places because this is a continuous function on a closed interval. You with me? Those are all the candidates, and the absolute max and absolute min have to occur there. Now, I don't know what the function value at 3 is, so I'm just going to call it the starting value. So we're just going to call this the starting value, which just SV, starting value. So at -3, we're at our starting value, whatever that is. I don't know what it is. It could be 10, it could be -5. I mean, I don't know what it is. We don't even know. But it's some starting value. Now, as we go forward, let's just kind of move forward to the number 1. We would take our starting value and we would add those boxes to it. So for at 1, it's going to be the starting value plus 6-ish. I'm just going to say 6-ish because, I mean, it's around 6. Okay, do you see where I'm going? Okay, so we've got the starting value at -3. We've moved to 1, and it's going to be the starting value when you add around 6. Whatever the starting value is, it doesn't matter. Whatever it is, you would add around 6 to it. Now, what happens when we get to 3? We would take our starting value, we would add 6-ish to it, and then we would subtract 2-ish from it, around 2. Why am I subtracting? Because that's the area under the curve. That has a negative sign. Okay, you see where I'm going with this? All right, so now we're at spot 4. So what would I do at spot 4? I would take my starting value and I would add 6-ish to it. I would subtract 2-ish from it, and then I would add 1-ish to it, somewhere around there. Now, with that information, we can figure out which is the very largest value comparatively. And we will say, for this to work, we will say the starting value is a positive number. Okay, so if I start at some positive number and I add 6, and let's see, so where is my very smallest number going to be? -3, at -3, right? That's going to be the very smallest y value, whatever it is, because all the other ones I'm adding stuff to. You with me? No matter what it is, it's the very smallest one. So we're going to say absolute min is at, and they just want the x coordinate because we don't know the y coordinate, at x equals -3. That's the absolute min. Okay, so then where would our absolute max be? Where do we think? 4, let's see, we add 6, we subtract 2, we add 1. So where does that put us? That would put us at 5, right? Because 6 minus 2 is 4 plus 1 is 5. So where should our maximum fall? At 1, right? Because that's just straight plus 6. So absolute max is at x equals 1. Now, you are not going to have a question like this on a free response that's so arbitrary, but I wanted to go through it with you so that you could understand the bigger picture as we pull in area, which we will later. Does that make sense? Okay, are there any questions?